From my experience, limiting reactants and excess reactants, which we'll learn about later, are literally the bane of every chemistry student's existence. So today we begin the journey of learning about limiting reactants and how we can calculate them. What are they and why do we care? By the end of this video, you should be able to solve for limiting reactants in two different ways, and you can kind of pick which option suits your needs the best, or which one makes more sense to you. And then you'll be able to use that knowledge to determine how much product is actually made, or theoretically is possible to be made, in a perfect world lab scenario. Before we jump into the math, let's think about this in context of a simple problem, like making s'mores on a camping trip. If you had 4 graham crackers, 1 marshmallow, and 8 pieces of chocolate, which ingredient there would limit the amount of s'mores you could make? Now, for those of you that have never had the joy of indulging in an ooey gooey s'more, you need 2 graham crackers per s'more, you need 1 marshmallow per s'more, and I personally like to take 3 little rectangles of Hershey's chocolate per 1 s'more. So given that information, what ingredient out of the list above would limit the number of whole s'mores that I could make? Go ahead and pause here to think about it. Hopefully you're noticing that if each s'more takes 2 graham crackers, I have 4, so I could technically make 2 s'mores if I had enough ingredients for 2 whole s'mores. But I only have 1 marshmallow. I have 8 pieces of chocolate, so if I needed 3 little rectangles per s'more, I'd actually have more chocolate than necessary. But the thing that limits my ability to make more than 1 s'more is the fact that I only have 1 marshmallow, and each s'more requires 1 marshmallow. So in this case, the limiting ingredient is my marshmallow. I can't make more than 1 s'more with just 1 marshmallow. So when we flip this thinking into chemistry, the reactant that gets completely used up, so there's nothing left of it, just like if we were to use the 1 marshmallow to make our 1 whole s'more, we wouldn't have any other marshmallows left. That ingredient is gone. That reactant is used up entirely, and that's what we call the limiting reactant, or LR. Again, that would be whatever ingredient would hinder you from being able to make a whole s'mores, or as in this image on the slide here, whatever is going to limit my ability to continue to make hot dogs. Here I have an excess of a leftover hot dog, the actual meat thereof, and I don't have enough buns to have another whole hot dog. So my limiting reactant, or reagent, as it's often called, would be my buns in that scenario, that I don't have enough buns for all the hot dogs that I have. Which I'm pretty sure is a conspiracy, by the way, because they don't give you enough buns in a single package of buns ever to fulfill all of the hot dogs you get in a package. So now back to this leftover thing. Whatever is left over, for example, from our s'mores, that would be the chocolate and the graham crackers. Those were left over. We would call those excess reactants or reagents, and I'm going to symbolize those as ER. In the case of the hot dog example, the excess would be the extra hot dog without a bun. So now if we were going to think about the limiting reactant in terms of moles, if we look at a balanced chemical equation where we have 2H2, 1O2 making 2 water molecules, and we were to look at this in pictorial form, so let's say we've got 1, 2, 3, 4 of those hydrogen molecules, and we have 1, 2, 3 of the oxygen molecules in some lab experiment. If I wanted to make water with that specific amount of reactant, as I showed in my balanced chemical equation, then I need to figure out, okay, well, how is water formed? Water has 1 oxygen, so that would have to split in half for each of these oxygen molecules. And per water, I have 2 H's. So that would hook up with this one. That one would hook up with this one. This one could hook up here, and this one could hook up here. So I could make a total of 4 water molecules, but I don't have any more hydrogens left to bond with that O2 molecule. So I end up just having that O2 molecule left over. So then what we can say is that the oxygen is in excess and the hydrogens, the blue stuff, got all used up. So there's no more of them left. That's like our marshmallow. That's like our hot dog buns. There's nothing left to continue making more water molecules. Therefore, this would be our limiting reactant. However, we don't always have pictures of molecules where we can just count up the atoms and see who paired with what. Therefore, we need to calculate for this. We need to be able to have a mathematical setup to calculate for this. So here we go. Let's jump into option 1. I mentioned at the beginning that there are 2 ways to determine a limiting reactant, an LR, and we're going to go the easier route, or what I perceive to be the easier route first, as option 1. So step 1 is to, of course, balance the provided chemical equation. Or if none is provided and you only have words, write it into the actual format, then balance it, or at least double check that the given equation is balanced before you proceed. That would be step 1 of option 1. Step 2 for option 1. In these types of questions, you'll be given at least 2 reactants and you'll be asked to calculate how much product could be made. So you're going to convert both of the reactants on 2 separate dimensional analysis problems into the grams of the product of interest. Now, sometimes they might not specify the grams of the product of interest. So if you still need to find the limiting reactant, just pick one of the products for your goal units and roll with it. Option 1, step 3 is now you've calculated from both reactants 2 separate dimensional analysis equations for the goal units of one of the products. Now all you have to do is compare those 2 product grams you calculated and figure out which one made less. Whichever product ends up being less amount, that reactant is the one that was the limiting reactant because it made less. Just like in our s'mores example, it made less with 1 marshmallow, therefore we knew the 1 marshmallow was the limiting reactant. We're just doing this with numbers now, that's all. And then that whole excess thing, well, by process of elimination, whichever reactant was deemed not the limiting reactant is the one that's in excess, the one that's left over. So let's give this a try then. It's sometimes easier to visualize this once we actually see it worked out step by step. We're going to calculate the amount of water for a combustion reaction. Methane plus oxygen goes to CO2 and water. If we had 20 grams of oxygen and if we had 10 grams of methane. We're trying to figure out how much grams of water could we make using that amount of reactant. Step 1 was to balance the chemical equation. So first things first, before we do any calculations, let's make sure that we compare our product side to our reactant side and see if we have a balanced equation. Right away, I'm looking at the hydrogens and I can see I have 2 on the product side and 4 on the reactant side. Let's balance that first. Let's put a 2 in the front here. So now I have 4 and I have 2 oxygens plus another 2 here. So I have 4 oxygens on the product side and I currently only have 2 on the reactant side. Let's fix that atom type now. We're going to put a 2 here so that I now have 4 oxygens. 2 times 2 gives me 4 on the reactant side, and I still have that 4 total on the product side. Let's check carbons. I've got 1 carbon here and 1 carbon there, so everything else is balanced. I've already set up the bare basic bones for you in terms of dimensional analysis conversions. I've put my magical line to freedom. I have an equal sign, a space for my answer, and my goal units at the end. I know that those are my goal units because it's asking me for the amount of water in the question. That's what I'm trying to solve in both cases because we're trying to figure out how much is actually created based off of the amounts of reactants we have of each. As always, when we're going from grams of one chemical to grams of another chemical, our pattern is going to follow a same and predictable pattern every time. We're always going to have our given as the first thing on the line. We'll have the molar mass of our given as the next thing. We'll have a mole ratio to convert from one chemical to another. And we'll have the molar mass of our goal chemical as the last thing in our dimensional analysis setup. This is always going to be the same pattern every single time. Since we've already put our given of 20 grams of oxygen as the first thing on our line, now we need to find the molar mass of oxygen. Where do we find that? On the periodic table. If we look at the little number underneath oxygen on the periodic table, you'll see it's 15.999. But I'm not going to torture myself and I'm going to round it to 16. There are 2 atoms of oxygen in an oxygen molecule, so 16 times 2 gives me 32 grams of O2 in 1 mole of O2. Now I need to get rid of that mole of O2. My grams cancel, but I'm stuck with this whole mole thing. In order to get rid of the mole O2 units, I'm going to use my mole ratio. And I find my numbers for mole ratios from the balanced chemical equations. That's why it's so crucial that you balance the equation first. So now I need to figure out how many moles of oxygen do I have? Well, I have 2, according to my balanced equation. And how many moles of water do I have? I have 2, according to my balanced equation. The goal mole goes on top. My goal is water. So I'm going to have my 2 mole water on top and my 2 mole oxygen on bottom. We can see that my mole of O2 cancels, and I am in fact in the right chemical category, but not the right unit. I still need grams and I have moles. To get from moles to grams, I'm going to use molar mass of water. In order to calculate the molar mass of water, I look at my periodic table and add up the parts. Each oxygen weighs 16 and each hydrogen weighs 1.008 times 2, because there's 2 of them in a molecule of water. 16 plus 2.016 gives me 18.016 grams of water per mole of water. My mole of water will cancel, and I am in fact left with my goal units. I know I did it right, so now I can plug and chug into my calculator. First, let's multiply across the top. 20 times 1 times 2 times 18.016 gives me 720.64 divided by 32 times 2 times 1, which is 64. When I divide those two, I get 11.26 grams of water is produced if I have 20 grams of oxygen. All right, now we have to do pretty much the same thing all over again, except starting with methane this time instead of oxygen. I have 10 grams of methane in this chemical reaction. I need to now find the molar mass of methane to get rid of the grams of methane from my given. Looking at the periodic table, we see that each carbon weighs 12.011 and each hydrogen weighs 1.008, and there happens to be 4 of them in a molecule of methane. So my molar mass ends up being 16.043. 16.043 grams of methane in 1 mole of methane. And now we can clearly see that our grams of methane cancels because we have top and bottom, just like our domino pieces will cancel out. And I'm left with moles of methane. To get rid of the mole of methane, I need to go back to my periodic table and find the mole ratio. In front of methane, there's an invisible 1. And I'm trying to also go to water, so I need to check out the mole of water, which is 2, just like before. So the 2 moles of water, the goal mole, goes on top, and 1 mole of CH4 on bottom, so that this mole will cancel with that mole. And I am now in fact left with the correct chemical, but still the wrong units. Notice that since we're calculating for the same thing we did before, the molar mass of water isn't just going to magically change from one to the other. We can save ourselves some trouble and just put the same piece in there as we already calculated. So that would be 18.016 grams of water in 1 mole of water. Notice that for these kind of calculation problems, this whole end piece right here is going to be identical every single time, because you're going to try and calculate for the same product every time to compare those final values together. So just keep in mind that the only thing that's changing is the reactant side of the dimensional analysis. Now that everything else is canceled in my dimensional analysis, and I am in fact left with my goal units of grams of water, H2O, I can plug and chug into my calculator. And that gives me 360.32 divided by 16.043. And I get 22.459 grams of water produced. My final step is to compare both of the amounts of water that I just calculated. I was able to get 11.26 grams of water out of 20 grams of oxygen, and I was able to get basically double that with 10 grams of methane. Well, whichever one gives me less product is the limiting reactant. So in this case, this value is much less than 22.459, and therefore the reactant that made that, the oxygen, is my limiting reactant. So in this case, oxygen must be my limiting reactant because it's the one that produced less water as the product. Just like with the marshmallow s'mores, I had 1 marshmallow only generating 1 s'more, therefore it was the limiting reactant. In other words, the maximum amount of water that could ever be made with these kind of specifications for an experiment would be 11.25 grams of water. absolute maximum, theoretically. And because oxygen is deemed the limiting reactant, by process of elimination, we can therefore say that the methane is the excess reactant. Now that you've seen it done once, go ahead and pause the video here and make sure you understand how to do this with the same chemical equation, but work it out with different amounts of reactant. Ready, go! Step 1 was to make sure that our equation was balanced. So just like we balanced the same equation before, there should be a 2 here and a 2 here. We need 2 separate dimensional analysis lines, so 2 magical lines to freedom. I'm just going to draw that right off the bat. I know I'm going to need 2. And we're trying to find the amount of water, so grams of water is still our goal, our end product. We're given now 2 different reactant amounts. We have 25 grams of oxygen, and we have 8 grams of methane. We know from before we found the molar mass of oxygen, which ended up being 32 grams of oxygen per mole. We found the mole ratio from the balanced chemical equation, so that was 2 moles of oxygen. That's on the bottom because my goal mole, my 2 water, goes on top. And then we needed the molar mass of water, which was 16 plus 2, essentially, so 18. I'm just rounding here. So 18 grams of water per mole of water. We'll see that our grams cancel here, moles cancel here, mole of water cancels here, and I am left with my units, so I know I did it right. Let's plug and chug in the calculator.
1 minute, 37 seconds later.
14.0625 grams of water could be made with 25 grams of oxygen. How about the methane then? Methane we already determined weighed 16.043 grams in 1 mole of methane. And from the balanced chemical equation, we found that all of this is going to be the same. But the thing that changes is my reactant side. I only have 1 mole of methane, so I should put a 1 here instead of a 2. But the rest of this is all going to be exactly the same as before. So 2 moles of water and 18 grams of water in 1 mole of water. Now plug into my calculator, which gives me 17.95 grams of water. So notice that in this question, I increased the amount of oxygen I had in the reactants and decreased the amount of methane, and yet still, in this case, my grams of water was less using oxygen as the reactant. So here, oxygen is still the limiting reactant. And the reactant that ends up making more than what's possible is methane. So methane, our CH4, is what we call the excess reactant. Now let's move on to what I consider to be the more challenging method. But if you'd like to use this method, if it makes more sense to you, here it is for you. Option 2 of learning how to determine the limiting reactant. Step 1 is to balance the chemical equation, just as it was before. Step 2 is to convert both of the reactants that you were given to moles using the molar masses. So basically the first thing we did in our dimensional analysis problem. Step 3 would be to continue converting the reactants, like reactant 1, into moles of the other reactant. So instead of finding grams of the product you're interested in, you would just convert it to moles of the other reactant using the mole ratio and vice versa. So instead of your goal being the grams of the product, your goal is now the moles of the other reactant. Then finally, you would compare the mole values of both reactants to each other. And now the way you figure out which one is limiting is that if reactant number 2 moles is less than the moles you were provided with, it's the limiting one, because you can't make more than what you were provided with. It's physically impossible. If reactant number 1 mole value is less than the moles you were provided with, then it's the limiting reactant. And just as before, whichever reactant is deemed not limiting is therefore the excess reactant by process of elimination. So for this option 2 method, let's give it a try. Step 1 is to balance the chemical equation, of course, as always. And now this is the same chemical equation we were just using, so let's just skip the formalities and put a 2 in front of here and a 2 in front of there, and we know it's balanced. Step 2 of option 2 is to then convert both of the reactants to moles. So in our question, we said, hey, we have 3.6 grams of methane and we have 5 grams of oxygen, both of our reactants. We're still going to have 2-dimensional analysis lines, but now we're just going to convert to the moles first of each reactant. So in this case, let's just go from grams to moles for oxygen. Just as we saw before, the molar mass of oxygen is 32 grams per mole. Therefore, my grams of oxygen cancels and I am left with moles of oxygen. And if I divide 5 by 32, I end up getting 0.156 moles of oxygen. And now for methane, just as we saw before, we had 16 grams of methane per 1 mole of methane as its molar mass. And we can see that the grams of methane cancel. We are left with moles of methane as our goal units. And if we take 3.6 divided by 16, I get 0.225 moles of methane. So now I'm just going to take these answers and start a new dimensional analysis line. So 0.156 moles of oxygen is now the first thing on my line here, and 0.225 moles of methane is the first thing on my line here. Of course, you could do this all in one step as well, but I'm breaking it up into steps so you can see where each piece is coming from. Now we need to convert both reactants to moles of the other reactant. So I was starting with moles of oxygen, and now I'm converting it to moles of methane. That's the other reactant in the equation. In order to go from moles to moles of one chemical to another, that's where I use the mole ratio. So again, let's take a look at our balanced equation. We had CH4 plus 2O2 forms CO2 plus 2H2O. So my mole ratio of oxygen and methane is 1 to 2. So now my mole of oxygen cancels and I am left with the moles of the other chemical, the other reactant. And we're just going to flip this ratio for the other way, because if we're trying to get from CH4 to O2, then I just need to flip that domino. And I end up with 2 moles of O2 over 1 mole of CH4, so that cancels and I am left with moles of O2, just like my goal says. When I take 0.156 times 1 and divide that by 2, I end up with 0.078 moles of methane. When I take 0.225 times 2 and then divide that by 1, which is essentially the same thing anyways, I end up with 0.45 moles of oxygen. Now comes what I consider the intellectually challenging or tricky part to this whole thing. You kind of have to compare what's on the given of this part of the step to the result to see which one runs out first. So let's look at this option 2, comparing values of step 4. So what this is essentially saying, if I can translate this for you, is that we need 0.078 moles of methane in order to react with 0.156 moles of oxygen. That is what would be necessary for the reaction to go to completion. So now what we have to say is, okay, well, were we given at least 0.078 moles of methane? Well, this is what we were given. So if we compare these two, we see that we need 0.078 moles of methane for it to happen, and we were given 0.225 moles of methane. Yes, we're in good shape. We definitely have more than enough methane in order for this to happen. Likewise, we could say, hey, we need 0.45 moles of oxygen to react with 0.225 moles of methane in order for this reaction to happen. Do we actually have that in the reaction? We were given 0.156 moles of oxygen, and we need 0.45. We don't have enough. So in this case, oxygen is our limiting reactant because we don't have enough of it. Therefore, our methane is going to be the excess reactant by process of elimination. So we've already used these values, 20 grams of oxygen and 10 grams of methane, so you already know which one is limiting and which one is in excess. But I'd like you to try it using this option 2 method of comparing moles from what we need versus what we were given. Go ahead and pause the video here to give this option of solving limiting reactants a try. Our balanced chemical equation, just as before, is still the same. It's still the same combustion reaction as we've had the entire time. And we know that we have 20 grams of oxygen and we have 10 grams of methane. And we're looking for how much water could be produced. If we're going to use option 2 to compare our mole values, we need to first start by converting our grams to moles of each reactant. All we need is our molar mass to convert each of the reactants to the mole of reactant we have. Just as before, CH4 weighs 16 grams per mole, and oxygen weighs 32 grams per mole. In our calculator, we're going to have 10 times 1 divided by 16 gives us 0.625 moles of methane. And for oxygen, we have 20 times 1 divided by 32 also gives us 0.625 moles of oxygen. So that was step 2. Now step 3 is to convert our moles of each reactant to the mole of the other reactant using mole ratios. So I'm just going to continue my line to freedom here, and my new goal is going to be mole of the other reactant. So here I have mole of methane, so my goal is going to be mole of oxygen. Just like here I have mole of oxygen, so my goal is mole of methane. Now I just need to use my mole ratios from the balanced equation to get from one mole to the other. I have 1 mole of methane from my balanced chemical equation, this invisible one up there, and I have 2 moles of oxygen. I'm just going to flip that ratio for the bottom dimensional analysis problem. So I have 2 moles of oxygen, 1 mole of methane. My moles of CH4 cancel here, my moles of oxygen cancel here. All I have to do is 0.625 times 2 divided by 1, which gives me 1.25. And for the bottom one, I have 0.625 times 1 divided by 2 gives me 0.3125. Now remember, over here, those were my given amounts. That's what I was given. Over here, this is what I need. So I need to compare what I need to what I'm given, or what I actually have in the reaction. So if I need 0.3125 moles of methane in order for the reaction to happen, and I'm given 0.625 moles of methane, I have enough methane for this to occur. I need 1.25 moles of oxygen for this to happen, but I only have 0.625 moles of oxygen. So since I don't have enough for what I need, the oxygen is my limiting reactant, and my methane ends up being my ER, or my excess reactant. Hopefully one of those 2 options appeals to you in order to solve for limiting reactants. Before you move forwards, onwards, and upwards, make sure you test yourself here. Pause the video and calculate the limiting reactant between 2 grams of Alka-Seltzer and 25 grams of HCl. How much table salt, NaCl, could be made, theoretically, using limiting reactants. If you'd like to check your answer, please comment below and I'll let you know if you got it right. Otherwise, hang tight for my next video and I'll work out this problem as a review before we go into excess reactants. Please give this video a quacks up if it was helpful for you, and please subscribe to my channel for more educational content. See you around!
No ducks, no glory.